Well, welcome to the disturbance portion of this morning's session. Anne mentioned the importance of forest in mediating snow. And the next two talks, I'll be talking about wildfire, and Polly will be talking about bark beetle. And wildfire is a perennial visitor to the Northwest. It's also part of the natural ecosystem. However, over the past few years, wildfire has been like an unwanted house guest who tends to stay a bit too long. We've seen between Idaho, Oregon, and Washington, we've seen 1.3 million acres burned in the last 3 years, each year at least. And in addition to that area burned, we've seen a number of very large fires. If you let me embellish the term mega fires, that's a little bit of an interesting term. But these are considered mega fires, these charismatic wildfires that take on their own persona, named sort of our equivalent to, tropical storms in many ways. And the work that I'll be presenting today is mainly work that's been done by my postdoc, Renaud Barbero, and also a former PhD student at University of Washington, Natasha Stavros. And the focus of our work is to understand the meteorological and climatological controls of these very largest wildfires, and it's really across the entire United States. And ultimately, to answer this question that I lay here before us is whether climate change will increase the probability of these fires going forward. We don't have to rewind the clock too far to recall some of these very large fires that we've seen across the Northwest. In 2002 in southwestern Oregon, the Biscuit Complex burned over 500,000 acres. And in 2007, we had a couple large complexes burning in central Idaho that each burned over 300,000 acres. And then, of course, this past summer, we saw the Carlton Complex, which is currently the largest wildfire seen in Washington State's history over the last 100 years or so. That fire burned over 250,000 acres in the sort of Okanagan Forest, east side of the Cascades, sort of abutting against between the forests and the rangeland, that transition zone, which probably is going to be an important area for disturbance. And a couple of things about these very large fires, besides the part that they actually get quite a bit of media attention, they actually commandeer quite a bit of suppression resources. We've heard in recent years the increasing number of dollars spent in fire fighting, hence leaving less dollars for the Forest Service and BLM to conduct other management practices. These fires also have local and direct impacts to the environment, as well as to property. The Carlton Complex here, I think, consumed 300 homes. And then the interesting thing about wildfire, which makes it an interesting hazard, is that you don't have to be actually living in an area where the fire occurred to experience its effects, because these fires, particularly fires that are burning in forested ecosystems, tend to burn over multiple weeks. And there can be chronic effects in terms of smoke on air quality, and over time, that has a chronic effect on human health. So the focus here today is to look at these very large fires. There have been a number of studies looking at climate-fire relationships. Most of the studies have looked at annual area burned. And the gist of our research is actually to understand these very large fires as part of a joint fire science project. We'll be doing this looking at these fires from a top-down perspective, so I'm not going to get into the details of how these fires might occur on smaller scales. So coming at it from looking at it from a climate and weather perspective, and that's our hypothesis behind these fires, is that they are principally enabled by climate and then driven by weather. And there's a couple of ingredients, maybe a few ingredients that you need for these fires to occur. You need to have widespread and abundant fuels, and it can vary depending on what sort of ecotype that you're in, if you're in a fuel-limited or a fire-limited or climate-limited ecosystem. Ignition sources are good, so lightning busts or anthropogenic sources. And then once a fire is ignited, a fire can be further driven by wind, and that particularly is the case more in some of the rangeland systems, or if there's a period of extreme fire danger, and this might be the case more so in the fuel-dominated forested ecosystems where these fires burn over multiple weeks. So we tried to define megafires, and this is problematic in so many ways. But what we did here is we looked at the monitoring trends in burn severity data set. It's a remote sensed way of assessing fire. And we basically looked at the top 10% of large fires. The MTBS database is only fires over 1,000 acres. So we consider the top 10 being our very large fires, the ones we wanted to focus in on. And it turned out that that was around a 30,000 acre fire. Okay? And then we also excluded the unburned to low category in the fire itself. These are satellite mapped fires, and so we excluded the areas that we considered maybe weren't burned at all. Again, we focus on the top-down drivers. This sort of analysis can be done at a variety of scales. It becomes statistically limiting because we're going to be looking at it through an empirical approach. And so we did this by ecoregion, and then we ended up lumping ecoregions together. And so the three ecoregions that I'll be generally talking about are grouped into the Cascades, basically the rangelands or the Northern Great Basin and the Columbia Basin, and then the Rocky Mountains and Blue Mountains. We used climate and weather data. The data came from both PRISM in terms of the climate data. You can see some of the variables that are listed there. We also used daily meteorological data from a data set that I put together that covers the period from '79 to present. And from the latter data set, we calculated fire danger indices. These are some of the metrics that are used operationally to determine firefighting tactics. They're also very much related to fire behavior. So some of the indices that I'll be talking about today include the energy release component, which is a good proxy for fire activity, and also the burning index, which is a good proxy for flame length. Most of the analysis that they'll be showing you hereafter is done at a 50-kilometer scale, and the reason for that is we're doing this. We actually did this over the entire United States, so what I'll show you today is really just for the Northwest, but it becomes quite a bit of data to be doing it at fine scales. So the first question is, do very large fires burn under anomalous conditions, or do they just burn under normal conditions? And the answer to that, what we did was we looked at composite analysis across a variety of variables. And what's being shown here are basically where we took all of the very large fires, greater than 30,000 acres, and we looked at the energy release component 20 days before the fire up to 20 days after a fire. And that's shown in red here. And then we looked at the other large fires between 1,000 and 30,000 acres, and those are shown in blue. And what you see basically is that there's a distinct difference between the energy release component of these fire danger indices for the very large fires versus the other large fires. So that gives us a good clue. These very large fires have a proclivity for burning when we have these extended windows of very, very low fuel moisture. This was really prominent in forested ecosystems. In rangeland ecosystems, it wasn't as dominant. And so you'll see some of that coming through in some of the modeling results. There was also an interesting dichotomous signal in the Palmer Drought Severity Index. Basically, these very, very large fires occurred during concurrent drought in forested ecosystems, whereas that was not the case in rangeland ecosystems. And that sort of comes back to some of the literature we know from Jeremy Littell and Tony Westerling involving pluvial conditions facilitating fire in the rangeland systems. So going forward from that, we developed a model, and the model was basically to try to model the probability of a very large fire. And we wanted to do this spatially and also as a function of time. And so we did this by basically week of the year, and we looked at pixels within each ecoregion. So we developed a model for each ecoregion. We considered the variability within an ecoregion in both across space and time. And then we basically developed these logistic stepwise regression models, and we did it through a resampling approach so that we weren't sensitive to particularly the data that we chose. And the models are shown here. Don't worry necessarily about what they show, but the one thing that we might want to point out is that these models basically all included temperature, weekly temperature as a predictive variable, and then they also all included basically a fire danger index, and then a couple other variables as well. Here's one application of our model to this past summer, mid-July, right? Mid-July, we actually had record heat across much of the east side Columbia Basin. The number of days above 70 degrees in Wenatchee was past an all-time record in terms of overnight lows. Impressive heat. The models ended up predicting a significant enhancement in the probability of a megafire right here along the east slope of the Cascades, and I've highlighted where the Carlton complex actually occurred, so that's maybe a nice example. We'll take this model forward and basically look at the climate projections, these downscaled climate projections, and insert them into the model, okay? And when we do that, we'll first review some of the projected changes. I showed you this before, but in the Northwest, we're projecting overall declines in precipitation, increases in temperature, and also we're projecting increases in the probability of very high fire danger. So if we recall back to one of the slides I showed you earlier, these fires tend to occur when we have these prolonged periods of high fire danger. In the future, we're projecting more that to occur more and more often. You can kind of see where this is going to go. So we did this across 18 models. The models all show something different. I'll show you that in a couple slides here. These are the results viewed through the lens of the multi-model mean, and the warm colors here all indicate increases in the probability relative to the late 20th century. So again, these are just increases projected by looking at top-down drivers. Okay, so we're not accounting for other factors in here. But what you see the strongest signal is basically in the Cascades. I will say, though, that Cascades historically have very low probability of these very large fires. So you can take that as you will. When we look at individual models, and we also, looks like I missed something didn't come through. But if we look at individual models and we compare the seasonality, what should be on the x-axis here is basically day of the year starting from May through October. The models all tend to show increases in the probability of a very large fire across the Northwest. This is for the entire Northwest. Some are higher than others, but significantly higher probability of very large fires and an extension of the window over which these fires might be able to occur. Here is some of the intermodal variability. So when sort of looking at climate change projections, I always advocate for using more models than you probably want to. And you can see the variety of responses here. The important thing to point out is that they all show increases in the probability of a large fire, anywhere between a doubling and one of these models is showing somewhere on the order of a 6-fold increase. But sort of the average is somewhere around a 3-fold increase in the probability of very large fires. So this is a statistical approach, and there are caveats to sort of statistically modeling fire. One of the caveats is that as fire increases across the landscape, you may come to a point where there's nothing left, right? So there is this idea of limited real estate. The other thing that's important to point out here is that we developed these fire-climate relationships using observations for the last 30 years. And we know that in the western United States, we have run up a fire deficit. Okay, so that's something to consider as well. There's some non-stationarity that's possibly built into those assumptions. The approach here doesn't allow us to look at specific types of synoptic weather patterns that are associated with critical fire weather. So things like dry cold fronts, lightning busts, wind extremes, offshore wind events. Those are things that we're not able to address. The GCMs are not necessarily the best way to go on assessing that. We did see yesterday that there's some evidence to suggest that offshore wind events might decrease just a tad. And then, of course, land management practices. These are things that we didn't have a time to address. And then, of course, I didn't show you anything on the west side of the Cascades, and that's a severe limitation when doing statistical modeling, is that we don't have that many large fires to deal with. And so there's a severe limitation in doing that. In addition to these statistical approaches, you can use dynamical global vegetation models. MC2 is a great example of that. And that might actually be able to overcome some of these limitations. And so I will end there by saying that very large fires in the Northwest tend to occur under these prolonged optimal burning conditions or wind events. And in terms of the projections, we're looking at an increase in the likelihood of these very large fires, something on the order of a 3-fold increase. And of course, those increases can be mediated by other factors, things that I didn't account for. So I think I'm through with my time, and I'll take any questions.
I was wondering, the highest probability is in the Washington Cascades, and I was wondering if you could comment on why that is.
Yeah, so certainly the highest probability is in the Cascades at large, and that all goes back to, have to make you look at an equation. It all goes back to this equation here, and if you look at the equation for the Cascades, and you look at the temperature actually has the highest coefficient there. So what we found was that historically, the strongest relationship between temperature and fire and large fire activity was found in the Cascades. And therefore, as temperature changes, that's where that sensitivity is going to be most acute.
Any other questions?
Is there a way of factoring in fire suppression generally? Because some places it's easier to suppress fires than others.
Yeah, no, that's absolutely right. And so, like, when you look at a map like this, there are areas where these very large fires have occurred and they're challenging to access in terms of fire suppression, distance from road, or other things like that. And that's, I think, where we're going to start to go next by refining this analysis down to more local scales and accounting for some of these geographic features, because that's obviously going to play a role.
We have another question.
John, great talk. On the looking to the future, where you were looking at the whole range of models, some of those models don't do a particularly good job of characterizing the temperature and precipitation in the Pacific Northwest. And I'm wondering, like, if you sorted through and found the models that were really good, would it constrain the variability more, and would you be able to maybe have a little higher confidence in looking to the future?
Yeah, well, that's a good question. So, my group has downscaled 20 models, and there have been studies that evaluated how well these models do in the Northwest. And one thing that we've done when we sort of, make those assessments on how well they do is we factor in all seasons. And so if we're dealing with fire in the summer, we actually might try to assess more specifically how well these models simulate summer climate. I think that might come into play. If I were to look at some of the models that I know are turkeys, bad models, I'm not sure if it would change this a ton, although that top model there I don't think is one I would necessarily use. But certainly those HADGEN models, I think, were mentioned earlier today. Those are decent models, and they show extreme drying over the region.
We have time for one more question. I think there were some people over here, or there's people waving their hands. You have the microphone. Go ahead.
I just had a question on the, right here, on the recurring fires in the same areas. I know there's been a lot of fires that have burned old fires, and is that I know in my previous life in the late 80s I did the Southwest or Northern California and Washington and Oregon, basically all over, but some of these areas are in Yellowstone, and some of these are, I guess, are due to burn again because of brush and stuff. How do we, I guess, factor that in, or make sure there's some management after it? Because a lot of times, the range stuff is we was still recovering from the '96 fire, and it just burned last year. So the range didn't have no chance to get the shrub step or any of that, and it's real unfortunate, but that's kind of the game going on right now.
Yeah, that's a good question. I mean, I think, and that comes into how we did the statistical modeling, but certainly, if you have the successional process occurring and you try to apply a model to a forest that's not quite a forest yet, then it might not come into play. I mean, these fires that have burned in the past can provide a barrier to fire spread. So some of the large fires that have occurred maybe tend to occur in areas that haven't burned for a while, although that may not be the case for the rangeland systems that are quickly responding.
Great. Well, thank you very much.